Hi everyone, welcome back. Today we are talking about ellipses as we continue our study of conic sections. An ellipse is, an oval. It's sort of a circle that's been smushed a little bit. So because of that, it's no longer got that rotational symmetry. So we could have horizontally aligned ellipses or we could have vertically aligned ellipses. So again, we'll have two different equations, whether it's a horizontal ellipse or a vertical ellipse. Notice that the only difference in the equations are the a squared and the b squareds, the positioning of them. Basically what that means are, if you take a look at the diagrams, a is the length from the center of your ellipse to what we call the vertex or the endpoints of the major axis, and that's so named because it's the longer of the two axes. It's the longer side. So the a squared is always going to be oriented along whatever variable is aligning that ellipse. So if it's a horizontal aligned ellipse, the a squared or the major axis measurement will be paired with the x values. X's are the horizontal ones. And if it's a vertically aligned ellipse, then the a squared or the major axis will be aligned with the y values. Otherwise, the two equations are exactly the same. The b value is the length of half of your minor axis. Your minor axis is your shorter axis, or your distance from your center point to what we call your co-vertex. The co-vertices are the endpoints of the minor axis or the shorter axis of the two. If it's a vertical ellipse, then the minor axis goes horizontally. Just like in parabolas, we have what are known as focus points, but in an ellipse we actually have two of them. The plural for focus is foci, which is a little bit obnoxious to say, but because we have two of them, we have to say it a lot. So I'm just putting that out there. C is the length of your focal length, or the distance from your center point to either focus. And the focus is always going to be aligned on your major axis. So it's always going to be on the same axis that your a value is. The last thing that you have to know about but is not on here is the latus rectum. Just like in a parabola, the latus rectum is the height of your conic section through its focus. So in this case, your latus rectum is always perpendicular, so it's going to be aligned up and down. But if you have a vertical ellipse, your latus rectum, which still needs to be perpendicular to your major axis, goes horizontally left to right. In an ellipse, we're going to calculate our latus rectum length by taking our a squared value, dividing it by our c, and doubling it. So it's a squared over c times 2. Okay, so there's a lot of information there, a lot of new vocabulary. The h and the k are still the coordinates of your center point. Graphing ellipses are super easy, easier than graphing parabolas. And really the most important thing to remember about the formula for ellipses is that a is always the major axis, and so therefore is always greater than your b. The last term we need to talk about with ellipses is what's called eccentricity. The eccentricity is a measure of its roundness or how closely it resembles a perfect circle. We calculate it by dividing our c by our a value. And the closer that that value approaches 0, the more circular it is. And as it gets closer and closer to 1, it means it's more eccentric or more oval or flat or less like a circle. Okay, so let's see how we could see this in different problems. So in example 1, it says to find the standard form of the equation of the ellipse having a foci at 0, 1, and 4, 1, and a major axis length of 6. So that gives us a lot of information there. So what I do with ellipses, just to keep, we have a lot of different measurements straight, is I make myself a little table every time. My A, B, and C are half the length of my major axis, half the length of my minor axis, and my focal length. And then the a squared, b squared, and c squared are simply those numbers squared, but those are the values that I need for standard form of my equation. I need my a squared and my b squared. So when they tell us that the foci are at 0, 1, and 4, 1, that tells us two important pieces of information. It gives us our c value, but it also tells us what direction our ellipse is going. And we can tell that this is horizontal because the foci are on the same axis as the major axis. And in this case, the major axis has to be moving horizontally because it's the x values that are changing. So from focus to focus, we have a distance of 4, which means that the focal length has to be half that, or 2. The major axis is 6, which tells us that our a value has to be half of that, which is 3. So based on that, we can get our a squared and our c squared. And to calculate our b squared, we can use this formula. C squared is a squared minus b squared. So if I rearrange that, then b squared is equal to a squared minus c squared. So I just need to subtract my a squared and my c squared to get my b squared. And I can find my b value, although I don't need it in this case. And then I can build my equation from there. The only other piece of information I need is my center point, which I can get from my two foci as well by finding the midpoint of the two foci. So halfway in between, I can find it by plotting the points and finding the middle point, or by using my midpoint formula. It's going to be at 2, 1, so I just plug my numbers in and get my standard form. Making sure that because it's horizontal, I put my a squared value under my x's. Okay, so here we're going to be sketching an ellipse. So I need to get it in standard form first, which means I need to get this side to be equal to 1. So I divide by 9 on both sides, but I don't want this coefficient here, so the next thing I do is I divide by that 4, which would cancel it out here, and then make this, if I divide my y squared by 4, it becomes 36. So from that, I can get my little table. My a squared is 36. This is going to be a vertical ellipse because it's with my y's. My b squared is 9. I don't need it in this one, but my c squared I could find out is 27, which makes my a and my b 6 and 3, which is what I need to graph my ellipse. My center is at 0, 0. And then from my center, my major axis, which is vertical, is up and down 6. So that's where these points came from, my vertices. And then my co-vertices, which are along the minor axis, I count left and right 3, whatever my b value is. And that's how I came up with that. So the vertices, again, are at 0, positive 6 and 0, negative 6. Oops. Okay. And we have another graphing problem in this, and we have to complete the square for this one. So I group my x's together, I group my y's together, and I put my coefficients on the other side. To complete the square of x squared plus 6x, I take my b value, I cut it in half, and then I square it. So to complete the square, I need to add 9. And over here, because of this coefficient, I need to factor that out first. And then I can complete the square now that I have no coefficient by taking half of my b value and then squaring it. So to complete the square here, I need to add 1. What I did on the left side, I have to do on the right side to keep my equation balanced. So since I added 9 here, I'm adding 9 here. And since I added 1, but really it was 4 times 1, I'm adding 4 times 1 over here as well. So now that I have complete squares, I can factor them to perfect square trinomials. So this becomes x plus 3 squared, and this becomes y minus 1 squared. Still have that 4 in the front. And when I combine my like terms here, I get 4. And then remember, we need to get a 1 over here, so I divide both sides by 4 now, which gives me x plus 3 squared over 4. These 4's cancel out, and I have equals 1. So I didn't make my little table of my a, b, c, a squared, b squared, c squared, but I can pull my center point from my equation. It's at negative 3, 1, so I plotted that. My major axis is going to be the horizontal, and it's 2. Or I should say not 2. The major axis is 4, but the a value is the square root of 4, or 2. So I count 2 to the left and 2 to the right. My b squared, I don't see 1, so it must be 1. We can always make something a fraction by putting it over 1. So the square root of 1 is 1. So I can count my minor axis, up 1 and down 1, and then connect all my points to get my ellipse. Okay. This one's very similar, except we're not graphing, we're just finding information about it. So they're asking us to find the center, the vertices, and the foci, so we need to get this into standard form. So again, we clump our x's together, we clump our y's together, we put our numbers over on the other side. We complete the square. In this case, because I have a leading coefficient, I factor that out first, and then I complete my square. This one, I can complete my square directly. Whatever I use to complete my square with, I need to add to the right side as well. I factor to get my matching binomial terms and combine like terms, and then divide by whatever this number is to get 1 over here on the right, which gives me a standard form equation here. So I can find my center by pulling it from the equation. My vertices are along the major axis. Remember, the major axis is vertically aligned, so I'm going to add my a value and subtract my a value to my y's. So my vertices are going to be up and down 4 from the point, from the center point, 1, -2. So that gives me -1, 2, and -1, -6. And the foci, which are also along that same axis, so I'm still affecting the x's and y, still affecting the y's. So I need to get my c value. Well, to get my c squared, I subtract these two, and I take the square root of that. So the square root of 12 simplifies to 2 square root 3. So my foci are going to be at 1, and then -2 plus 2 square root 3, and -2 minus 2 square root 3. And then finally, this last problem, example 5, is an application of where you would see an ellipse problem in real life. A lot of orbits in space are elliptical. They're not circular, or not perfectly circular. So they're talking about the orbit of the moon around the Earth, which is slightly elliptical. And they want them to know the distance of the apogee and the perigee. The apogee is the greatest distance of the moon from the Earth, and the perigee is the closest distance. So basically, if you can see from the diagram, it's essentially, since the Earth is just off the center, it's essentially half the major axis plus the focal length, and half the major axis minus the focal length. So we need our a and our c values. So I got my a by cutting my major axis in half. I got my b by cutting my minor axis in half. So then I needed to find my a squared and my b squareds by squaring both those two numbers, really big numbers. I get my c squared by subtracting those two. And then I got my c value, or my focal length, by taking the square root. So now to find the apogee, which is the furthest distance, I took my a value and I added the c value. And to find the perigee, I took my a value and I subtracted the c value. And that was it. Please take a look at the assigned work, and remember that I'm here for you on Thursdays, or really any other time by appointment, if you have any questions and you need anything clarified.